Good morning to all. In Annamalai University Directorate of Distance Education, we have M.Sc Mathematics program. In the first year, we have abstract algebra paper. This abstract algebra is divided to 5 units and 10 lessons. Before going to the lecture, I will introduce myself. I am Dr. J. BOOBALAN, Assistant Professor, Department of Mathematics, Annamalai University, Annamalai Nagar, deputed to Manmu Dr. Purachi Thalavar MGR Government Arts and Science College, Kadamanar. Now we give a brief introduction about the units. And this abstract algebra paper is divided into 5 units. Unit 1 deals with the group theory, and Unit 2 discusses about group theory in detail. Unit 3 discusses about ring theory, and Unit 4 is about ring theory continuation, and in Unit 5 we have a ring theory along with vector spaces and inner product spaces. The content and treatment as in the book Topics in Algebra by A.N. Hestein, John Willey and Sons, 2002. We have a reference books into Algebra by Michael Artin, Prentice Hall of India, New Delhi, 1994, and Lecture in Abstract Algebra, Volume 1 and 2 and 3 by N. Jacobson, D. van Amsterdam and Co., New York, 1976. In lesson 1, we have introduced some basics. In this lesson, basic notations of sets and mappings, Cartesian product, binary operations, permutation and its degree, equivalence relation, partial order relation, equivalent classes, and are discussed with suitable examples. Objectives: first, sets and mappings, set and product, Cartesian product, binary operations, permutation and its degree, equivalence relation, partial order relation, equivalent class are explained in detail. Objectives of this lecture is sets and mappings, setting Cartesian products, binary operations, permutation and its degree, equivalence relation, partial order relation, equivalent classes are explained in detail. First, we have defined definition of a set, and then mapping and Cartesian product, binary operation, definition of permutation and its degree, definition of equivalence relation and partial order relation, definition of equivalent class, etc. We define now the set. The union of two sets A and B is written as A union B is equal to X such that X belongs to A or X belongs to B. Is a set, and the intersection of A and B is written as A intersection B is equal to X such that X in A and X in B. Now, for any two sets A and B, the difference is A minus B such that X in A but X not in B. Now we give an example for these things. If I have A is equal to 1, 2, 5, 6, 7 and B is equal to 1, 2, 3, 6, 8. Then our A union B is equal to the elements which are belongs to both A and B, that is 1, 2, 3, 4, 1, 2, 3, 5, 6, 7 and 8. Now our A intersection B is the common elements between A and B, that is 1, 2, 6. That's it. And again our A minus B is equal to the elements which belongs to A and not belongs to B, that is belongs to A is 1, 2, 5 and not belongs to B, that are 5 and 7. That is these elements 5 and 7 are in A but not in B. And for example, we give a B minus A also, the elements which are belongs to B but not in A, that is 5 and 8. In B and but not in, that is 3 and 8. Okay. Now we give the universal set with a complement A dash is equal to x minus A. X is the universal set and A is the set defined. Then we have some basic properties regarding the union and intersection and complementation. Suppose we have property A union B is equal to B union A and A intersection B is equal to B intersection A. This is called commutativity property. And this property will be applicable in a commutative group or abelian group. And this part is involved in definition of a group, particularly for abelian group or commutative group. Then we have a second property called A union B union C is equal to A union B union C, and A intersection B intersection C is equal to A intersection B intersection C. This is called associative property. Associativity with respect to union and intersection. Then we have a distributive property. Left distributive and right distributive are here. A union B intersection C, A union B union C is equal to A union B union A union C. Similarly, A intersection B intersection C is equal to A intersection B intersection A intersection C. This is distributive with respect to union and intersection. Then we have complementation. A union B whole dash is equal to A dash intersection B dash. Similarly, A intersection B whole dash is equal to A dash union B dash. This is De Morgan's law. Now we define Cartesian product. Cartesian product is nothing but it is given in ordered pair. let A comma B are two given sets, then their Cartesian product is defined as the set just of all ordered pairs, as I already told, are in ordered pairs. Ordered pairs of A and B, where the small a belongs to capital A and small b is in capital, small b is in capital B. The Cartesian product denoted as A cross B is given in ordered pair. We denote the pair A1 comma B1 to be equal to A2 comma B2 if and only if A1 equal to A2 and B1 is equal to B2. Now we define mapping. A mapping from one set S to another set T is a rule that associates with each element with each element small s in capital S is a unique element small t in capital T. Now let phi be a mapping from S into T. We often define this by phi such that S goes to T with the mapping phi, comma, if the small t belongs to capital T is the image of S in capital S under the mapping phi. We represent this fact by Pi of s is equal to small t, the set of all pi images of the element of capital S will be denoted by the symbol pi of s. Now we have equality of mappings, definite equality of mappings. Two mappings pi and f of s into t, two mappings pi and f of capital S into capital T are said to be equal if and only if pi of s is equal to f of s for every small s belongs to capital S. Next we give another definition. The mapping pi such that S goes to T is said to be onto if for a given small t belongs to capital T, then there exists an element small s in capital S such that pi of s is equal to some small t. And onto mapping is also called surjective. Is also called surjective. If a mapping is both one to one onto, then it is called bijective. Now we move into next definition. One to one and onto are said to be bijective. And inverse mapping also we give if inverse mapping, if f is such that s goes to t is a one to one and onto, then inverse mapping f inverse is such that t goes to s is given by f inverse of t is equal to some small s, where f of s is equal to some small t. Composition of mapping. Then we define composition of mapping. if my pi is such that s goes to t and another mapping theta which is maps t into u, then the composition also known as the product of pi and theta is the mapping theta dot phi such that s goes to u is defined by theta dot phi of s is equal to theta of pi of s for every s belongs to capital S. We now give some properties. Property 1, pi such that s goes to t and theta such that t goes to u, then we have the following results. Theta dot phi is onto if both theta and phi are onto. Then we have second property, it is necessary onto. Onto if theta dot phi is onto. Then we have a third result, theta dot phi is onto both theta dot phi is onto 1 to 1, sorry, 1 to 1 if both theta and pi are 1 to 1. Next we have result called necessarily 1 to 1 if pi is necessarily 1 to 1 if theta dot phi is 1 to 1. Next we have a second property, if pi is such that s goes to t and theta is a mapping which maps t into u and psi is a mapping such that u goes to c, then psi dot theta dot phi is equal to psi dot theta dot phi. Similarly, we give property 3. That is, if phi such that S goes to T be 1 to 1 and on to mapping, and pi inverse is the inverse of pi, then pi inverse dot pi is equal to identity. This it, small it, I take, and pi dot pi inverse is equal to small is, where I t is such that t goes to t, or identity mappings. This is both 1 to 1 and on to, so this is called bijective. Now we move into binary operation. Bi means 2. Binary operation means between two elements one operation must be there. That operation is called binary operation. A binary operation on set S is a rule which associates for every ordered pair of elements A, B in S and element C in S. Thus the mapping is S cross S, which is goes to capital S. Permutation and its degree. Now we will define permutation and its degree. A bijective mapping on a finite set capital S is called permutation on S. The degree of the permutation is nothing but the number of elements in the finite set S. In the finite set S, the set of all permutation of the set S on n elements is denoted by Sn. it may be seen that the number of members in the set S is n factorial. If S is a set with A1, A2 up to An, then a permutation of S is sometimes conveniently represented by the symbol A1, A2 up to An and AI1, AI2 etc. up to AIN, where I1, I2, IN are the integers are arranged in some order, where I1, I2 up to IN are integers arranged integers 1 to up to n arranged in some order. Now we define a relation R. The relation R is defined by, on a set S, the relation R is defined on a set S as an ordered pair of elements A comma B in S, such that A has a relation R on B. We write A relation B if A has the relation R on B. Then we have types of relations. R, ST, reflexive, symmetric and transitive. A relation A, this is reflective. A relation B, which implies B relation A, this is called symmetric. And if A relation B and B relation C, then we have, which implies A relation C, that is called transitive. If these three properties are satisfied, then it is called as an equivalence relation. This reflexive, symmetric and transitive yields equivalence relation. Now we define equivalence class. If S is a set and if capital R is an equivalence relation on S, then the equivalence class of A in S is the set equivalent class is given in square bracket. Equivalent class of A is equal to set of all x in S such that this A relation x. Then we move into name some terminal exercises. It is given up to you. Now we move into group theory. The unit lesson 2 in our core unit 1 group. First let us define a group. Before that we already given a definition on binary relation. First group, let we define the group with let G be a non-empty set and let star be a binary relation in G. Then we have the following properties. First, A comma B in G implies A star B in G. This is called closure property. If A comma B comma C belongs to G, then we have A star B star C is equal to A star B star C. This property is called associative. Suppose in the third one, A star E is equal to E star A is equal to A. This is called identity property. Then our fourth property is A star A inverse is equal to A inverse star A, which is equal to E. There is a relationship between this identity in identity and inverse property. If this non-empty set G satisfies the above four conditions, means then it is called as a group. Okay, let G be a group and a non-empty set. Let G be a non-empty set. Let star be a binary relation in G. Then we must say that G is a group if it satisfies the above four properties. Now we give an example. Suppose a set of all integers with respect to addition is a group. We check this by satisfying four properties. First one is closure property. Suppose I have to take in set of all integers Z, we have take 1 comma 2 in Z. Then the binary operation here is addition, so that we have to put this addition here. 1 plus 2, which is equal to 3, which is belongs to set of all integers. So the closure property is satisfied. Now we move into the associative. Suppose I take 1, 2, 3 are elements in the set of all integers. Then we have 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. This is the associative property, that is 6 equal to 6. Then we have identity property, 1 plus what is equal to 1, that is 0. 0 is the identity element. Therefore, this yields the identity property. Now we have inverse. Here the 0 is the identity element. Then we have inverse property, 1 plus minus 1 is equal to minus 1 plus 1, which is equal to 0. This identity comes here in inverse, so that these four properties are satisfied. So it is an example for the group. Now we quickly move into that abelian group or a commutative group. If a group satisfies commutative property, then we must say that it is a commutative group or abelian group. The group G with the binary operation star is called abelian group or commutative group if A star B is equal to B star A for every A comma B are elements in G. Example for this, the previous set of all integers with respect to addition is example given. So that example is also valid for this particular abelian group. Suppose we have take 2 comma 3 in set of all integers, 2 comma 3 in a set, then 2 plus 3 is equal to 3 plus 2, which is equal to 5 equal to 5. Now I give you a remark. With respect to addition, the identity element is 0. Whereas in the case of product, suppose we take the product set of all integers with respect to product. For this product, the identity element is 1. Clear? Now we move into the next definition. Subgroup. Before that, we give a problem. As a checking for the multiplication of real numbers with respect to forms a group of order 2. Next example, let G is equal to 1 comma minus 1 under the multiplication of real numbers with respect to multiplication, G forms a group. S3, the set of all permutation of 3 elements forms a group. Yeah, we now take a problem. Let G be a non-empty set closed under an associative operation and satisfy the following. There exists an element E in G such that A dot E is equal to E for all A in G. Given A in G, comma, there exists an element Y in G such that AY is equal to identity E, then G is a group under this product. We give a solution for this particular problem. To prove there exists identity, and suppose if we have an element Y, then A dot Y is equal to identity. It is defaultly we have to prove, so that we move into the another problem. Let G be a non-empty set closed under an associative operation and satisfies the following. This is one important problem. There exists an E in G such that A dot E is equal to A for all A in G. Next property, for given A in G, there exists an element Y in G such that A dot Y is equal to identity E, then G is a group under this product. Now we check this one. To prove G is a group, we have to prove 4 properties, but we have the identity is given and the inverse is also given. Is sufficient that to prove this is a group, to prove G to be a group, it is sufficient to prove on E is also a left identity, that is E dot A is equal to A is equal to A dot E for all A in G. Second one, all right inverse is also a left inverse, that is A dot Y is equal to E is equal to Y dot A is equal to E. First we shall show that if AY is equal to E, then YA is also equal to E. By the property 2 in this particular problem, this one, for a given Y, we can find Y1 in G such that Y dot Y1 is equal to identity. Consider YA Y1 which is equal to YAY Y1 which is equal to Y AY is equal to identity here, so that we say that this AY is equal to E. Therefore, YE Y1 which is equal to Y Y1 which is equal to identity. This property is clear. But YA Y1 is equal to YA Y1 which is equal to YA into E which is equal to YA, because this Y1 is equal to E. Therefore, YA is equal to some E. This YA equal to E we given here. Hence, AY is equal to YA is equal to E. Therefore, all right inverse is also left inverse. We also know that both the left cancellation law and right cancellation law are true in group theory. Now, we have AE is equal to A. Just now we proved that for a given A, there exists a Y in G such that we have A dot E is equal to A. Just now shown that for a given A, there exists y such that ay is equal to ya is equal to E. Therefore, all right inverse also is equal to right inverse left inverse. Hence, EA is equal to AY dot A is equal to A into YA, which is equal to A into E, because AY is equal to E and YA is equal to E. Thus, E is a left identity. Now we move into that subgroup. Let G be a group with respect to product. If we have H is a subset of G, H is said to be subgroup of G if H itself forms a group under the same binary operation. Here the binary operation product under dot, then H is called the subgroup of G. Example, suppose H is of even integers and G is of all types of integer, set of all integers with respect to both addition and subtraction with so then H is a subset of this G with respect to the same binary operation addition. H is also a group, G is a bigger group, so H is a subgroup of G. Now we have a problem. We have to check the validity of this problem. If G is a group with AB whole power I is equal to A power I dot B power I. For 3 consecutive integers, of I, for all AB in G, then G is abelian or commutative. As we already know, commutative property is nothing but it satisfies the property A dot B is equal to B dot A or A plus B is equal to B plus A. We recall that. Now we have the solution. Let a dot b whole power I is equal to a power I dot b power I as given. This is for 3 consecutive integers. It may be ab whole power I plus 1 is equal to a power I plus 1 dot b power I plus 1 is the second one, second integer. I take the third integer as a power I plus 2 is equal to a dot b whole power I plus 2 is equal to a power I plus 2 dot b power I plus 2. This is the third one. With this, we have to prove that a dot b is equal to b dot a. We have to bifurcate this into a dot b whole power I plus 1 into ab, which is equal to a power I plus 2 dot b power I plus 2 as given here. Now we have to take ab whole power I plus 1 into ab is equal to a power I plus 2 dot b power I plus 1 dot b. As I already told, both the left cancellation law and left and right cancellation law are valid in group theory. So we have to take this element out. Left b and left b are cancelled. So we have ab whole power I plus 1 into a is equal to a power I plus 2 b power I plus 1. Yeah, this is the remaining thing. Then we have a dot b whole power I into this a b power I plus 1 is equal to a power I plus 1, so a power I into b power I into ba is equal to a power I plus 1 into b power I plus 1. By left cancellation law and right cancellation law, we have this one. ab whole power I into ba is equal to this a power I into b power I is equal to ab whole power I into ba is equal to ab whole power I into ab. This we have to cancel, but remaining thing is ab is equal to ba. So this is abelian group or commutative group. Some problems are given. We left out these things and moving to the next part. As I told already, using subgroup, we have given lemma. Subgroup is nothing but if G is a group with respect to the binary operation product, H is a subset of G, then H itself is called a subgroup of G if H itself forms a group under the same binary operation dot with respect to, so that we say that H is a subgroup of G. We recalled that. Now we move into the lemma. A non-empty set subset H of G, H of a group G is a subgroup of G if and only if symbolically we give this symbol. If and only if first case A comma B in H implies that A dot B in H. This is called closure property. If A in H, we have A inverse in H. This is inverse property. A non-empty subset H of a group is called subgroup of G if both of these properties are satisfied. Now we prove this one. As I already told, a group is consisting 4 properties wise: closure, associative, identity and inverse. First let us take these 2 properties are valid. So rest of the 2 properties are associative and identity. Inverse is in this part means that it is consisting that identity also. Identity and inverse are mutually related. So that we move into this one proof. If H is a subgroup of G, first let us assume that properties 1 and 2 are true. So we have to justify that associativity and identity property are exist in this particular problem, so that we may say that H is a subgroup of G. So clearly associative is there means closure is there means associative will also be there. Associative, third property, associative will exist. Associativity will exist, since if associative closure property is not there means closure associative property is not in this particular case. And we may also say that inverse property exists means it has the identity also. So by this way we say that it is a group. Conversely, let us assume that H is a subgroup of G. Then we have to show that the 2 properties wise closure and inverse will hold. To show that H is a subgroup, we have to show that associative law holds in H and associativity is identity exists in this particular case. So we have if A in H by property 2, A inverse also in H, since A in H implies that A inverse in H, that is the property 2. So by property 1, by 1, that is A comma B in H implies that A dot B in H. So that if we connect these 2 things, A dot A inverse in G in H. So A dot A inverse is equal to E in H. Therefore identity will hold. Therefore by 2 property 2, the inverse belongs to H. Thus, H is a subgroup of G. This proves the theorem. With this, we end up this session. We will back in the next session. Thank you. Sir?